So for exponential growth, and you can read the details of how this is derived in the materials, I just have the result displayed here. We get a mathematical function which is called the exponential function. Its formulation is given in that yellow box here. The population number at any time point that you would like, can be calculated as the product of two things. The first is an initial population at time equals 0, which we call n naught. We have already seen we need to define something to start with. So once given an initial population, you can then multiply this number with the mathematical exponential function. And if you hand it as an argument this product k times t, then you will be able to calculate the population and predict it for just any time points without need of simulation. So we need to look at k times t. What is k times t? T we know already. T is our continuously advancing time. Now, just as a real number, so can take any value, not just in steps of doubling time or steps of 1, because we're not doing simulations anymore. And k is something that we can derive mathematically from the fractional growth 1 plus r that we used before. And there's a very simple conversion, which is given down here. You can calculate this factor k by taking the logarithm of what you had previously defined as 1 plus r. So taking this information, we can now enter our code by, first of all, defining our k. It's certainly something that we need to do. We need to find out what is the value of k if we want to use it later. And we were told it's the logarithm of something. And the logarithm is taken over r plus 1. So we can just put in the value that we had found previously. If I go to my command window, I can check if it's still there. R plus 1, yes, it's still there. It's equal to 1.0353. So the value still being there, we can use that. Assign the value of k by having this logarithm taken of it. And of course, now we can define our exponential function as given before. So how did we define our exponential function? First of all, we define the variable. And keep things simple. We have only our variable t. That's our time advancing. So we define that with the at symbol. And we can now put in our function as n naught, our initial population, times what? Times the exponential function in MATLAB is abbreviated exp, and provide its argument, which we were told is k times t. So I plug in k times t, and that should define our exponential function. What we can check is, do we know the value of n naught already? I've just put in n naught, but it's not defined. Why is it not defined? Because actually we never define it. We just said n of 1. So that's maybe not such a good idea to take n of 1, because n of 1 refers to that time point 1. And we said we want it to be independent of time points. So what we can do is, rather than taking a specific, we just define the value that we want to start with and assign it to a value. And in this case, we might just take n of 1. We might just say we can put in equals 0, or we take n of 1, or whatever we choose. If we choose it to be the same, and we define it here. So I can comment this. We have our initial population, and we have defined our value of k here. And we now can define function, and in this case it's now for exponential growth. how can we conclude this? Once we have defined our function for exponential growth, we can use our, if I comment this, make our plot of it. We can use fplot to plot it, apply that to our function, which in this case is called 1. And if we need to define the range over which we want to plot it, then we can use the previous limit, which I think we called nt. If we just go up and see nt was the length in time points, if we want to plot it over the same range as before, then we check what is nt. It's 121, so we can have it run over the time point nt minus 1, and then we would have it run from 0 to 120. Actually, we started from 1 to 121, so if we take this away, it will just be fine, because now we're starting at 0 rather than 1. So we define our k-value, we define our anonymous function as the exponential growth function, and then we try to plot it. And if we execute this piece of code, we can see we're getting a now continuous line from that anonymous function that describes our exponential growth in place of the original discrete time calculations. If we wanted to overlay the two plots, then I think that should be the final thing that we want to do. So we can overlay our plot with what we had done previously in our discrete time simulation, our model simulation in steps of 1, except we don't want this new plot to be erased, so we call that hold on. We hold on, we tell MATLAB to not erase the previous plot, execute the previous code again to get our discrete time points, and we can see that indeed the simulation and the mathematical function coincide. So the simulation follows exactly the mathematical function in a way that gives us confidence that the simulation can also be used to make good prediction into the future. If I use the MATLAB tool for zooming into the plot, it's in the upper left side, and that symbol that looks a little bit like a lens. And we can go and see what does it actually look like, and we can see these simulated bullet points go exactly through that line that is the output of our mathematical function.